I'm Glen Darling from the IBM Edge Application Manager team, and I'd like to tell you everything you've always wanted to know about IEAM. So in this presentation, I'll talk about our original motivations for developing the software, our driving tenets, and then give you a brief overview of our architecture. So what is IEAM? Well, it's IBM's commercial distribution of the Linux Foundation's Edge project called Open Horizon. And Open Horizon is fleet management for containerized software and data files. So it supports most kinds of standalone Linux hosts with 512 megabytes of RAM and up. So that includes x86 64, ARM32 v6 and up, v7, LE, and HF, and ARM64 v8, and PPC 64 LE, the IBM Power Architecture. And it also supports most types of Kubernetes clusters. So you can manage your containerized software on all of these platforms. Our very small, fully autonomous agent runs on each node, driven by the policies that you set. The agent does not bind or listen to any external ports, so you can firewall it. And all of the components offer rich REST APIs, and there's a CLI too for easy access, and the IBM version adds a graphical web UI for interaction. We also have secret management, so you can securely deploy credentials to your edge machines, to the workloads that you run on your edge machines. And we have secure device onboard, which enables zero-touch install. And really, all you do is connect the power and network and walk away, and the appropriate software will be automatically installed and configured for Edge Application Manager and for whatever particular task you've assigned that machine to take. We also enable independent life cycles for your code and your large data files, and this is designed for machine learning models, etc. So you can update your neural network model without any disruption to your service. Just bring in the new model and switch over between inferences. And all of this software is open source except for the graphical web UI. It's open sourced as the Linux Foundation Edge project, Open Horizon, and you can take a look at the link there for more information about Open Horizon. So why did we choose to make this thing? We noticed three trends back in about 2014, 2015. First of all, tiny things. They're faster, cheaper, and more capable. And one of the earliest machines that started to speed this revolution was the Arduino line from Italy. These were just little 8-bit CPUs, and they were about $30, and you could connect them and do all kinds of amazing things with them, and it was open source hardware too. Then in 2014, it really took off with these little devices from a company called Espressif. And these are about $1 at retail, and they have 32-bit CPUs, and they're able to go to sleep at less than 10 microamperes, which means that you can take a couple of AA batteries and run this thing for a year. And it has Wi-Fi built in and really powerful little computers for just $1. Then they, over the years, have improved on those too, and there are newer machines like the ESP32 on the right that's twice as fast and has Bluetooth Low Energy for communications, which is really great. Then 2011, the Raspberry Pis had come out, and they have been growing many different models since then. There's just a few of them shown on the screen here. 0W was previously the small workhorse for this family, but now there's the 02W, which costs a little bit more, $15. But it's got the 64-bit CPU instead of the ARM32 v6 in the Raspberry Pi 0W you see there. But there's also several A models like the 3A Plus that's sitting there, and several B models like the 4B that's shown on the right. The 4B models go all the way up to 8 gigabytes of RAM with a 64-bit CPU. So quite powerful, very small, easily used computers. And NVIDIA also came out with some interesting machines. These nano machines on the left are now only $60, and they contain an NVIDIA GPU, which means that they can do incredibly fast inferencing right on that little machine. And if you're willing to pay more, you can move up to something like the Xavier NX, and there's even a model above that that have the NVIDIA Volta GPU. That's you know, desktop or data center GPU from just a few years ago, but it's available in this very small form factor now. And of course, many other companies make small machines, and we were seeing them proliferate long ago. But these two are just two that I happen to have in my hardware collection at my house here. One is the Dell Edge Gateway. It's got all ruggedized components, and the ports are all covered. And there's a little HP machine that you often see in retail and medical application areas. Um, Small machines everywhere. And there are more of them than us. The Earth today has about 8 billion people approximately, and there are about 50 billion internet connected computers. And that number is expected to achieve 500 billion by 2030. Those numbers are from Cisco Systems. But most of the data created in these machines is never captured, analyzed, or acted upon, and 60% of the data loses its value within a few milliseconds of being generated. So the last major change we saw happening was containment, and I think it's the future of all software development. And here's a little bit of motivation on that too. So let's talk about containerized products in the real world. ISO standardized intermodal containers like the ones you see on this ship in the mid 1960s. And today, over 90% of non-bulk international transport is shipped on these containers. And for softer wares, for your programs, Linux containers have similarly revolutionized data centers. Docker really accelerated this starting in 2013. So let's synthesize all of those pieces, how we chose to put it together. So in the middle of the last decade, we noticed rapidly increasing computational power and tiny low-cost network-connected machines at the edge. Exponential growth in the volume of data at the network edge. Exponential growth in the number of machines at the edge. And machine inferencing was starting to happen on small edge machines. And at the same time, the Linux container revolution was sweeping across public clouds and business data centers. But we also noticed rapidly increasing risk at the edge as both the quantity and sophistication of cyber warfare increased. And there were a lot of botnet attacks around that time where entire collections of IoT devices were being pressed into service by malevolent actors. So we defined some guiding principles for our solution to this problem. First of all, we insisted that it must have technological, economic, and social merits. And the data volume was growing faster than bandwidth to the cloud. So we have to change this model where the edge devices just pump data up to a cloud. It's not going to work as the number of devices and the volume of data increases. So we want to turn high volume, low value data into low volume, high value data by doing some analysis locally on the machines. So local code with policies will also enable low latency actions. So you take a stimulus and you turn that into a response right there on the machine, and that can occur within a millisecond often. And edge machines will be able to run ML models locally to make these decisions and act. So very sophisticated analysis can be taking place, like object detection or speech recognition kinds of activities can take place in the very tiny edge machines now. Local software and large files will need to be updated. And this is typically difficult in the field after initial deployment, and a lot of IoT devices just don't get updated properly, and this leads to vulnerabilities as exploits are discovered over time. Also, the model of centralized control with dumb machines, it simply enables botnets. And so our view is that edge machines need to be autonomous to prevent botnets. And we also feel that autonomous machines will actually outnumber people. And so scale is a very major concern. And with all these autonomous machines out there, they will combine and interact in new ways that will create new value. And we wanted to anticipate that as well. So our decision was to build an open and decentralized solution to foster innovation, which is, of course, what happened with x86 PCs, with IP networking, with Linux itself, and to facilitate multi-vendor, multi-tenant solutions. And we'll open source our software and establish an edge ecosystem. So this is what our architecture for this looks like. We use Linux containers, and we support any Docker-compatible repositories. It's decentralized with autonomous, untrusting edge node agents. And just as a side note, our original version of this used only peer-to-peer technologies. So we use the Ethereum blockchain for discovery and negotiation. We use BitTorrent to transfer files from place to place, and Whisper for communication between the different agents. And we were not able to achieve the scale that we wanted using those technologies, so we did add a centralized core. We have a minimal central management hub to enable this scale, but we kept the idea of decentralized design and untrusting agents. So every component has a very small scope of authority, and this minimizes the risk of any kind of systemic compromise like a botnet. The zero trust model with certificates, encryption, and cryptographic signing is everywhere in our solution. We also preserve the privacy of the edge nodes. Even the IP addresses of the edge nodes are kept private for most of the components in the system. And we allow independent life cycles for code and data files like those large ML model files. What we found in our early experimentation is that although the inferencing software itself did not change very often, the ML models changed a lot. We'd retrain them and deploy them again, retrain them and deploy them again. So we felt it was important to have independent life cycles for the code and the data. We also want to minimize human work because of this scale. So we use zero ops and zero touch wherever possible in the design. And what you do is state your intent using something we call policy. Then the agents go ahead and autonomously make it real across your entire fleet of machines. So let's look a little more closely. How does it work? We have an autonomous agent on each edge machine or cluster. We support Kubernetes clusters as well, and it will keep working even when disconnected from the network. And so one advantage of that is that it can roll back a version on failure based on your rollback policies, even without a network connection. And we have a central management hub that has an exchange, which is really just a shared database of metadata for the items that you publish into IBM Edge Application Manager. And we use it for rendezvous between the agents and other components. And then we have some agreement robots, or what we call agbots, that collaborate with the agents, and but they're located in the central management hub. Then we have a switchboard, and this is a blind mailbox service for the agents and agbots to communicate, and I'll talk more about that in a bit. And there's a model management service, which is what enables the independent life cycles for your data files, and a secrets manager to allow you to securely distribute credentials to edge services. We're integrated with HashiCorp's Vault for that. And we have a rendezvous server that you can optionally use for secure device onboard, although typically when you purchase a secure device onboard machine from a manufacturer, the manufacturer will provide their own rendezvous server. But if you want to create your own secure device onboard devices, you can use our rendezvous server. And we have a web UI, the IBM version does, and that's a graphical UI that complements the CLI and the REST APIs that all of the components provide. So let's see how these pieces fit together to work. So here's the Management Hub, and the I'm calling it the Open Horizon Management Hub here, but it really is the IBM Edge Application Manager Management Hub, because at the bottom I have the web UI that is provided only in the IBM version. And of course, you need some Docker compatible container registries to put your containerized software into, and you can have multiple of those. Each individual container that you publish can be in its own unique registry, if you like. And then you need some edge computers. So this first one here is an SDO computer, a secure device onboard computer, and they always come with an ownership voucher, which is a key for that machine. And the SDO software is installed in the factory for these machines. And like I said before, you can make your own. You can install the SDO software and create your own ownership vouchers if you wish. And then this is another way to go, just any old edge computer. And like I said, we support a wide variety of architectures and operating systems. So if you have your own edge computer, you'll need to install the agent, and that includes the ESS or Edge Sync service, which is part of the model management system, in order to turn it into an Open Horizon Edge node. So let's take a look at a couple of typical onboarding scenarios for bringing your edge machines into this system. So let's start with a secure device on board. This is the easiest way to bring devices on board. So to begin, when you bought your SDO computer, you got an ownership voucher for it. You register that ownership voucher with the exchange. You don't have to do anything with the computer itself. You just have to take the ownership voucher and register it as a proxy for the computer in the exchange. Then the exchange will reach out to whatever rendezvous server is specified in the ownership voucher. So it reaches out to either the local one in our management hub, or it can reach out to the manufacturer's rendezvous server. And after that, you don't need the voucher anymore. Then in the field, when that machine powers up, the SDO software will reach out to its rendezvous server, which could either be the one in the hub or the one that the manufacturer provided. And it knows, because the exchange has told it what software to install on the computer and how to configure it for this particular management hub, and also what role this computer will have within the IBM Edge Application Manager, and that is specified by policy. So it'll register the machine and install all the software and configure it with whatever policies you want for this machine. And that's all done very securely using hardware device attestation, if it's available, to prove that this machine is exactly the machine that is supposed to receive that software. And at the end of that, you have your agent registered and ready to go on the Edge node, and we'll talk more about how it does other things once it's registered. But now let's take a look at the manual onboard process if you just have a regular computer that does not have secure device onboard. So for that one, you have to connect to the console or SSH into the computer over the network, and then you have to configure your credentials for Open Horizons Management Hub or IEAM's Management Hub. And then you download and run our agent install script. And the result of that is a registered agent configured with whatever policy you specified when you registered it. So once a machine is registered, when you register it, you can choose it to either be registered with a pattern or a policy, and there are other videos that can explain the difference between those. But policy is the underlying foundation of both. Deployment pattern is a simplification to make it easier for beginners to start with. And the policies that you set into the agent, they will govern the behavior of the autonomous agent for the rest of its life. And you can change them too using the credentials that you have for this specific node. So after your agents are registered, how are they managed? Let's look at that. The Edge machine can be completely firewalled. No ports are open on the agent. There are no listeners. The agent you cannot reach out from the outside world to communicate with the agent at all. And so that's what enables you to firewall it. Instead, the agent reaches out to the exchange and to the switchboard whenever it needs to communicate. And the only port that you need to open for that on the management hub side is the HTTPS port 443. So the agent, as long as it's able to make an HTTPS connection to the management hub's address, it can do all of its communications through that mechanism. The agbots also look at the exchange to discover that the agent has arrived and to get the public key of the agent so it can communicate with the agent. And then it can use the switchboard to send messages back and forth with the agent that are encrypted with the private key of the agbot and the public key of the agent. And the agent sends messages encrypted with its private key and with the public key of the agbot. And so that communication is encrypted in a way that both the agent and the agbot can understand, the two that are communicating with each other, but the switchboard cannot understand. So these agents will then make their own decisions based on the policies that you've set for them, and they'll communicate with the agbots, whose role is to collaborate with the agents to make sure they know about things that have changed in the exchange and so on. All of the communications are encrypted, and the agents are known only by their public keys. And the agent agbot communications also use perfect forward secrecy, which just means that each message uses a unique key that they each independently generate. So the switchboard cannot read or insert communications between the agents and agbots. It's private between them. Also, the agents independently pull their images from any set of Docker-compatible registries. So the agent is the one that reaches out to get the software too. Note that the management hub is not involved at all in that part of the process, and this helps to achieve great scale. And also, each container can be in its own registry. Then the containers, data files, and deployment are all cryptographically signed by their authors. So the agent in the field will verify that this container has not been modified and that the deployment information, which is things like where the agent can access the file system of the host, or which ports it's allowed to, your container is allowed to bind to, and whether it should run with particular capabilities or privileges. All of that is cryptographically signed when you deploy, when you set your policies and procedure or patterns for your deployment. Each agent independently verifies those things, and the agent is also able to fall back on old versions when something goes wrong, even without a network connection. So one more little detail: how do you deploy your software? So here's our developer, and she's going to push some containerized software to a Docker compatible registry first. So you have to containerize your software, so using commands like docker build, docker push. And then you need to cryptographically sign and publish your Open Horizon service description. So you use a command like hzn exchange service publish to publish a containerized software collection to the exchange to make it available for deployment to edge nodes. Then you use software deployment patterns or deployment policies to configure your agents to pick up that software and install it and run it. And then optionally, the developer can also use our model management system to similarly deploy those large data files, which do not need to be containerized. So quick summary: the agents are autonomous and they can be firewalled. They don't open any ports. Nothing ever initiates contact with the agents. The agents always initiate contact. So the agents reach outward, and this prevents any malevolent actors from reaching into the agent. Edge node IP addresses are private for security and privacy. So even if you know which node, you don't know its IP address, so you don't know its location physically on the planet. It's good for privacy and security. So all code and all data files and all deployment details are all cryptographically signed. It's a highly decentralized system, so it scales extremely well. And the agents continue to function when they're disconnected from the management hub or from the internet altogether. And all communications, even between the internal components within the management hub, are encrypted. And the agent Agbot comms have additional protection by using perfect forward secrecy. And a compromised management hub cannot take control of the agents. So remember that botnets were one of the things we really wanted to try to do our best to prevent. So even if you take over the management hub, the management hub cannot tell agents to run their own software. And just a reminder that IEAM is IBM's commercial distribution of this open source, Open Horizon, which has open governance. We'd love to have you come and join our open project. So now you know everything. Well, almost. And if you want to learn more to see why IEAM is better than all the rest, I'd suggest you check out Policies and Patterns. There's a video on that. SDO, which is the Secure Device Onboard, there's a video on that too. And the Model Management System, there's a couple of videos on that. And there's Secrets Manager, Security, lots of information out there you can get more details on. So if you're ready to learn more, the IBM Developer YouTube channel has an Open Horizon playlist, an IBM Edge Application Manager playlist. And there's a URL on the left there, and you can just hit this QR code. And there's also on the Linux Foundation's YouTube channel, there's a playlist for Open Horizon that has a few more videos that look at this from the open perspective. And if you are interested in the IBM Edge Application Manager official documentation pages, there's a URL and a QR code for you. And finally, if you're interested in the product itself, you can go to our IEAM official product page. Thank you very much for listening to this video. And if you need any information, you can reach out to me at glendarling@us.ibm.com.